Okay, the last part of our lesson involves proving identities. And in proving identities, we're going to write some variations on the trigonometric identities that we used. So for instance, you'll remember the one that we are all going to memorize, sine squared of theta plus cosine squared of theta is equal to 1. And we can write two variations of that Pythagorean identity that might be useful to us. If we subtract sine squared of theta from both sides, then we'll have an identity that will look like this. Cosine squared of theta is equal to 1 minus sine squared of theta. If we were to subtract instead cosine squared from both sides, then we'd have sine squared of theta is equal to 1 minus cosine squared of theta. Now we're just going to think through dividing the original Pythagorean theorem by cosine squared of theta and sine squared of theta. If we divide each term by cosine squared of theta, the first term is sine squared over cosine squared, which is tangent squared. The second term is cosine squared over cosine squared, which is 1. And that's equal to the third term, which is 1 over cosine squared, which is secant squared of theta. We can write two variations of this. If we were to subtract 1 from both sides of the equation, we would get tangent squared of theta is equal to secant squared of theta minus 1. If we were to subtract tangent squared from both sides, we would get 1 is equal to secant squared of theta minus tangent squared of theta. Okay, our third Pythagorean identity comes from dividing the original by sine squared of theta. Sine squared of theta divided by sine squared of theta is 1. Cosine squared of theta divided by sine squared of theta is cotangent squared of theta. And 1 divided by sine squared of theta is cosecant squared of theta. If we subtract terms from both sides of that equation, we might come up with a variation cotangent squared of theta is equal to cosecant squared of theta minus 1. We also might come up with a variation 1 is equal to cosecant squared of theta minus cotangent squared of theta. When proving identities, these variations can be used. Okay, so now let's prove, instead of an algebraic identity, let's prove a trigonometric identity. In the first of these, I think we can all agree that the most complicated side is the left side, so that's the one I'm going to start with. So the first thing that I'm going to do is I'm going to copy that side. Cosine of theta times cosecant of theta times tangent of theta equals, and I'm not going to write 1. If I wrote 1 at this point, I would be saying that I have now proven the identity, which I have not done yet. So we can do some re-expressing. There's not much I can do with cosine of theta, so I'm just going to leave that one alone. I can rewrite cosecant of theta as 1 over the sine of theta. I can also write the tangent of theta as sine of theta over cosine of theta. Now at this point I can grab my handy-dandy red cancellation pen, or perhaps the blue one, and cancel the sine factors and cancel the cosine factors. What's left? 1. So we've now proven the trig identity, and you may choose to write QED after that if you wish. It's not required. Okay, in B, I think we can agree that the left side of the equation is more complicated. So let's start with that one. 1 plus cosine of theta times 1 minus sine of theta equals, and we're going to re-express it. I'm sorry, I miscopied that one. That was 1 minus cosine of theta. And we're going to continue to re-express that until we get sine squared of theta. So I think the first thing that we probably ought to do is to FOIL. When we multiply two binomials together, we can use the FOIL method. The product of the first is 1 times 1, which is 1. The product of the outer functions is negative cosine of theta. The product of the inner terms is positive cosine of theta. And the product of the last is a positive times a negative, so negative cosine squared of theta. All right, let's add some like terms. You'll notice that we have a minus cosine theta and a positive cosine theta, so they'll add up to 0. Those terms will go away. And we're left with 1 minus cosine squared of theta. Now you remember that was one of our variations on the Pythagorean identity. 1 minus cosine squared of theta is sine squared of theta, because sine squared of theta plus cosine squared of theta is equal to 1. All right, in C, we see an expression with natural logs in it. Now, of course, you're going to remember from Algebra 2 that there is a property of logarithms. It's true of any base, but I'll write it with natural logs. The natural log of A plus the natural log of B is equal to the natural log of A times B. That's a property of logarithms that we can use. So in C, we can take the natural log of the secant of theta plus the natural log of the cotangent of theta, and we can re-express that as the natural log of secant of theta times cotangent of theta. So next, we can re-express secant of theta as 1 over the cosine of theta, and we can re-express cotangent of theta as cosine of theta over sine of theta. Grab your cancellation pen. So that would be the natural log of 1 over sine of theta. And we know that 1 over the sine of theta is the cosecant of theta. In D, we can start with 1 minus cotangent squared of theta. I'm sorry, 1 minus cotangent of theta, the quantity squared. And when we square a binomial, it's easier if we write out the binomial times itself and then FOIL. The product of the first is 1 times 1 is 1. Outers minus cotangent of theta. Inners minus cotangent of theta. And lasts, a negative times a negative will give us a positive cotangent squared of theta. I'm going to rearrange the terms and put our 1 and cotangent squared of theta as the first two terms. And then we can combine together negative 1 times cotangent theta and negative 1 times cotangent theta to get negative 2 times the cotangent of theta. Now you may remember that there's a Pythagorean identity that states that 1 plus the cotangent squared of theta is equal to the cosecant squared of theta. That's one of those Pythagorean identities that we can develop from sine squared plus cosine squared is equal to 1 and divide through by sine squared. So we can replace the 1 plus cotangent squared with cosecant squared. Oops. Cosecant squared of theta minus 2 times the cotangent of theta. And we've reached the end of our proof because we've just proven that 1 minus cotangent of theta squared is equal to cosecant squared of theta minus 2 cotangent of theta. Okay, 2 more examples. In E, we have cosine of theta times the cotangent of theta plus the sine of theta. That needs to be transformed into the cosecant of theta. So I'm going to take cosine of theta, leave it alone, and re-express cotangent of theta as cosine of theta over the sine of theta. And there's not much I can do with sine of theta for the time being. Okay, so when we take and multiply cosine of theta times cosine of theta over sine of theta, that gives us cosine squared of theta over the sine of theta. Now we're going to try to add that to sine of theta, but before we can add them, we need a common denominator. So you might start by rewriting sine of theta as sine of theta over 1 and multiplying both the top and the bottom of that fraction by sine of theta. That'll give us a common denominator of sine of theta. So when we add our 2 fractions together, they'll have that common denominator of sine of theta, and the numerator will be cosine squared of theta from the first fraction plus, and then add the second fraction's numerator, which would be sine squared of theta. Now cosine squared of theta plus sine squared of theta is always equal to 1. That's one of our Pythagorean identities. And then last, we can re-express 1 minus sine of theta as cosecant of theta. And now we're done with the proof. Last example, we can start with cosine of theta plus cosine of theta times the tangent squared of theta. And our task is to transform that into the secant of theta. So I'll re-express, there's not much I can do to re-express this, but what I can do is I can factor out a cosine of theta from both terms. If I factor out cosine of theta from both terms, from the first term we'll have a 1 left, and from the second term we'll have tangent squared of theta left. Now, there's something that we can do to replace that 1 plus tangent squared of theta. So let's take a little detour over to the side and remember our Pythagorean identities, because since tangent is squared, that makes me think that we might use our Pythagorean identities. So I know that sine squared of theta plus cosine squared of theta is equal to 1. And we can divide all terms by cosine squared of theta. And that will give us tangent squared of theta plus 1 is equal to secant squared of theta. So that means that tangent 1 plus tangent squared of theta can be replaced with a secant squared of theta. Since our goal is to write this in terms of the secant function, I'm going to change the cosine into 1 over the secant of theta. Secant squared of theta can be written as secant squared of theta over 1. And then when we multiply those two fractions together, we'll get secant squared of theta over secant of theta. One factor of secant will cancel from the numerator and denominator, and that will leave us with secant theta. Since we've reached our goal, it has now been proven.